Hello, everyone. Tonight we're going to embark on a journey not to some distant star or forgotten land, but to a place we inhabit every single day without ever truly seeing it. The living, breathing atmosphere that wraps our world like a soft, invisible blanket. I want you to imagine for just a moment that you are not sitting or lying in a room, but are floating weightlessly, a tiny speck at the bottom of a vast, gentle ocean of air. We'll drift on quiet currents, explore the invisible tides, and feel the softest whispers of the wind, all in a peaceful descent toward slumber. Now I should give you a gentle warning. While this journey is designed to help you unwind and ease into rest, there's always the small risk that it might be just interesting enough to keep you listening. But if you do end up wide-eyed at 2 in the morning, thinking about atmospheric layers and the weight of air, well, at least you'll be a little smarter for it. Now, before you go and watch, please take a moment to like and subscribe to this video, but only if you truly enjoy what I do. And if you're comfortable sharing, I'd love to know where in the world you're watching from and what time it is for you right now. The first thing to understand about this great ocean is that it has a floor, a surface, but no ceiling. Its upper boundary simply fades away, thinning into the vacuum of space. The air you are breathing right now is not a limitless substance. It is a fluid, a vast and gently swaying sea of gases, and like any ocean, it has depth and character. We live at the very bottom of it, and the weight of all the air above you is pressing down on every single part of your body. It's an enormous weight, a historical truth that civilizations have been trying to understand for millennia. Think about the ancient Egyptians. They believed the sky was a goddess nut arched over the earth. This was a poetic, almost theatrical way of describing the immensity above. But it was only in the 17th century, with the invention of the barometer by a student of Galileo's named Evangelista Torricelli, that we could finally begin to measure that weight, that atmospheric pressure. He demonstrated that the air had weight and that it could support a column of mercury. This was a revolutionary concept, proving that the sky was not just an empty void, but a tangible, measurable force. It's a fun fact, a little piece of hidden history that most people never consider as they go about their day. Now imagine that we are slowly, gently rising. You don't feel a single thing, no turbulence, no sensation of movement. You're just ascending. As you float upward, you pass through the layers of this magnificent fluid. The lowest layer is the one we're all familiar with, where all the drama of weather plays out. This is the troposphere. It's where the clouds you see from your window form, where the rain falls, and where the wind whispers through the trees. It's a very thin layer proportionally, like the delicate skin on an apple, yet it contains more than 3/4 of the entire atmosphere's mass. It's where all the weather we care about actually happens. Most airplanes cruise at an altitude of 35,000 feet, which sounds incredibly high, but you're still well within this thin dynamic layer, and you've already risen above a huge chunk of the air below. Think about that for a moment. Most of the air you'll ever interact with is contained within just a few miles of the Earth's surface. As you continue to ascend, we leave behind the chaotic, stormy troposphere and enter a new world, one that is calmer, colder, and far more serene. This is the stratosphere. It stretches from about 7 miles up to around 30 miles high. In this layer, the air becomes so thin that if you were there without a pressure suit, your blood would boil, a strange and unsettling truth of physics. But it's also here that you find the ozone layer, a delicate shield of molecules that protects life on Earth from the sun's more energetic and mischievous rays. Without this shield, our planet would be a very different place, bathed in a type of light that would make life as we know it impossible. It is in this layer that the air actually warms as you go up, which is counterintuitive. But it's because the ozone layer is absorbing all that solar radiation, turning the atmosphere itself into a warm and gentle blanket. Drifting higher still, you pass through the mesosphere. The name comes from the Greek word for middle, and it is indeed the middle layer of the atmosphere. Here, meteors, those bright streaks you sometimes see in the night sky, burn up in a brilliant display of friction, This layer is fiercely cold, the coldest of all the atmospheric layers, with temperatures dropping to nearly 130 degrees Fahrenheit. It's a quiet, high-altitude graveyard for space debris, a place where cosmic stones meet their end in a flash of light. You might wonder as you float through this cold and empty space how something so seemingly fragile can protect us from the constant bombardment of cosmic travelers. The answer is in its density. Even at this altitude, the air is thick enough to act as a shield, a silent guardian that keeps us safe. Your gentle ascent continues, and now you enter the thermosphere. The name means heat sphere, and it is a place of extremes. Here the air is incredibly thin, but the temperatures can soar to thousands of degrees. It's a paradox, isn't it? It's hot, but it wouldn't feel hot to you. This is because heat is a measure of the energy of molecules. And while the individual molecules here are moving incredibly fast, there are so few of them that they wouldn't transfer enough energy to your body for you to feel their heat. The thermosphere is also where you will find the International Space Station, a tiny human-made outpost orbiting in a region where the atmosphere is so thin that it is barely more than a whisper. It's also the realm of the auroras, the spectacular light shows that we see near the Earth's poles. These shimmering curtains of light are caused by charged particles from the sun, the solar wind colliding with the molecules in our atmosphere, and the thermosphere is the stage for this magnificent cosmic ballet. The shimmering reds, greens, and blues are a silent visual symphony played out for those lucky enough to witness it. Finally, at the very edge, the atmosphere becomes almost impossibly thin, so tenuous that the last molecules of air are in constant danger of being lost to space. This is the exosphere, the outermost layer. Think of it as the whispery fringe of our planet's great blanket. Here, molecules are few and far between, and their individual journeys are long and lonely. Some are held in a gentle embrace by Earth's gravity, while others drift off into the cosmic beyond, lost to the silent, starry vacuum. It is here that the ocean of air ends, not with a sudden stop, but with a slow, graceful dissolve. As you begin your gentle return, sinking back through the cold and then the warm, you come to realize that this atmosphere is not just a stage for weather, but a character itself. It's made mostly of nitrogen, about 78%, and oxygen, about 21%, with a small dash of other gases that are crucial for life. The ancient Greeks, historians remind us, had a different understanding of this. They believed that air was one of the 4 fundamental elements of the cosmos alongside fire, water, and earth. To them, it wasn't a cocktail of gases, but an ethereal substance that connected the divine to the mortal. This view persisted for centuries, a testament to how our understanding of the world is shaped by both poetry and science. Historians still debate whether early civilizations had any inkling of the air's tangible weight, or if they saw it as a purely spiritual, unmeasurable force. But regardless of what they believed, they knew instinctively that it was vital to life. It's the air that makes our world a world, not a barren, lifeless rock. This atmosphere behaves in fascinating ways. It flows, it swirls, it tumbles, and it reacts to changes in temperature and pressure. Warm air tends to rise because it's less dense. Cold air sinks because it's heavier. This simple principle, warm air up and cold air down, is the very heartbeat of all weather. Think about it. The sun warms the earth, but it doesn't do so evenly. The equator gets a lot of sunlight, while the poles get very little. Land warms faster than water. All of these differences create pockets of warm and cold air, and because nature absolutely loves balance, the atmosphere is always trying to even things out, creating movement, and with it, the dance of weather. Now imagine a sunny patch of ground, maybe in a small town in California. The sun has been baking it all day. The air above that spot begins to rise, and as it rises, it cools. Cooler air can't hold as much moisture, so if there's water vapor in that rising air, it condenses into tiny droplets. What are those tiny droplets? They're clouds. Meanwhile, the surrounding cooler, heavier air rushes in to take its place. This simple, elegant movement is called convection. It's the same principle that helps cook a roast dinner or move bubbles through a pot of boiling soup, just on a much, much bigger scale. And all of this rising and falling, this movement and stillness is happening right above you right now. It is a system that is not just alive, it's lively. It's a system that never sleeps, never rests. Even on a calm, cloudless day, there are quiet currents of air slipping past you, subtle changes in humidity, and invisible dances of temperature gradients. It's all part of this continuous quest for equilibrium. The Earth is a restless sphere, wrapped in warm gases, dancing with sunlight and spinning through space. And every gust of wind, every cloud, every raindrop is part of this continuous quest for balance. And as you settle deeper into your own quiet space, know that all of this whole swirling, ever-changing engine runs without a single switch or command. It is self-organizing, driven by the elegant poetry of physics. Gravity holds it close, sunlight stirs it, and the golden rule of thermodynamics ensures that energy will always try to spread out. The air we breathe, the clouds, we see the winds that blow, it's all a great planetary ballet, choreographed by sunlight and stirred by gravity. And it all begins right here in the air we breathe, a fact that is as humbling as it is comforting. You are not a spectator to the atmosphere. You are a part of it, held in its gentle embrace. Every breath you take, every soft sigh is an exchange, a conversation with the invisible ocean above. And that is a very beautiful thing indeed. Let the weight of all that air above you feel not like a burden, but like a soft, constant presence. And as the last of those thoughts drift away, just notice the air around you. How still is it? How quiet? Or can you feel the faintest movement, a subtle breath of the world? It's all there waiting for you to notice. A single, quiet, elegant system. And now let us turn our attention to the great choreographer of this atmospheric dance, the sun. This star, some 93 million miles away, is not merely a background actor, but the ultimate puppet master of every wind, every cloud, and every drop of rain. Without it, Earth would be a cold, dark rock with no wind, no clouds, and certainly no weather apps warning us about scattered showers that somehow manage to completely drench our socks. The sun's energy, which arrives in the form of sunlight, technically electromagnetic radiation, is the single largest driver of all weather. It is a constant, gentle push that sets the entire system in motion. But here is a delightful, quirky fact. The sun does not heat the atmosphere directly. Instead, it heats the ground, the oceans, and everything resting on the planet's surface. These surfaces, in turn, radiate warmth back upwards, heating the air above them. So, it's not sunshine warming the air directly. It's the Earth radiating warmth back. Think of a stovetop heating the air above it after being turned on. This simple principle is the source of all the grand atmospheric motion, a truth that feels both profound and intimately familiar. When you feel the warmth of the air on a summer day, it is the energy of the Earth itself lovingly released back into the sky. Because our planet is a sphere and tilted on its axis, some regions receive a generous solar spotlight, while others have to make do with a dimmer glow. The equator, for example, receives sunlight more directly than the poles. This leads to a beautiful and persistent imbalance. The tropics warm up quickly, while the polar regions remain chilled. And when there's an imbalance, nature does what it always does. It tries to smooth things out. The result is motion. Constant, beautiful atmospheric motion. Warm air near the equator rises. As it does, it creates an area of lower pressure near the surface. Air from higher pressure regions flows in to fill the gap. Meanwhile, the rising air moves aloft and eventually travels toward the poles, cooling as it goes. At higher latitudes, the air descends and starts moving back toward the equator near the surface. This large-scale circulation is known as a convection cell. Because the Earth is large and round, And we humans love to name things. We've identified 3 main convection cells in each hemisphere. Nearest to the equator is the Hadley cell. Above that, in the mid-latitudes, lies the Ferrel cell. And near the poles, there's the polar cell. Together, these cells help redistribute heat from the equator toward the poles, keeping the atmosphere circulating like a giant invisible conveyor belt. It is Earth's great gentle sigh, a constant adjustment that ensures the whole planet doesn't become too hot or too cold. Within these cells, we find major wind systems that have shaped human history. Near the equator, for instance, there are the trade winds, reliable easterly winds that blow from east to west. Sailors have used these winds for centuries to cross oceans. A common historical fact is that these winds in a way powered the age of sail, allowing explorers to navigate vast stretches of open water. One could almost say the age of exploration was powered by wind and ambition in equal measure, though historians still debate whether early sailors had a truly scientific understanding of these global patterns, or if they simply relied on passed down knowledge and a feel for the prevailing currents. Moving a little farther from the equator in the mid-latitudes, we find the westerlies winds that blow from the west toward the east. These are the ones responsible for pushing weather systems across North America and Europe. And farther poleward, we encounter the polar easterlies, cold, dry winds that blow from east to west near the Arctic and Antarctic. But here comes the next delightful twist in our weather tale, the Coriolis effect. Because the Earth spins, and in fact, it spins very fast, over 1,000 miles per hour at the equator, anything moving over its surface, including air, gets subtly nudged off course. This isn't because the air has feelings or stage fright, but because of physics. Picture this: the Earth rotates fastest at the equator and more slowly near the poles. If air moves from one latitude to another, it brings along its rotational speed. This mismatch causes it to deflect. In the northern hemisphere, it curves to the right. In the southern hemisphere, to the left. The Coriolis effect doesn't make air spiral like a toilet flush. It's not that dramatic. But over long distances and timescales, it has a profound effect on wind patterns. It's why cyclones spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere, and why global wind systems form those neat, consistent bands rather than chaotic spaghetti-like messes. It's the universe's little nudge, a reminder that nothing moves in a straight line for long. If you zoom even farther out, you'll find another powerful influence on our weather, the jet stream. These are narrow bands of fast-moving air, like high-altitude rivers, snaking their way high above us at the boundary between major air masses. The most well-known one is the polar jet stream, which flows between the cold polar air and the warmer air of the mid-latitudes. It typically sits around 6 to 9 miles above the surface and can reach speeds of over 200 miles per hour. That's faster than most sports cars, though, thankfully, with fewer tailgaters. Jet streams form where there are strong temperature contrasts in the atmosphere. Think of them as rivers of wind silently steering weather systems across continents. When a jet stream dips or rises, it can bring cold snaps or heat waves, influence storm development, and make weather forecasters either very happy or extremely nervous. It's a constant meandering path, one that can subtly change the fate of your afternoon picnic. This hidden influence has a delightful consequence for modern-day air travel. If you've ever flown from west to east and noticed your journey was shorter than the return trip, you've likely caught a ride on the jet stream. It's the atmospheric equivalent of a moving sidewalk, only much, much faster. Now let's step back and consider our journey around the sun. The Earth isn't just spinning and warming and jet streaming. It's also tilted, by about 23.5 degrees to be precise. This tilt is what gives us seasons, a slow, predictable rhythm that governs the mood of the entire planet. As the Earth orbits the sun over the course of a year, different parts of the planet receive different amounts of sunlight. When the northern hemisphere is tilted toward the sun, it experiences summer. The days are longer, and the sun is higher in the sky, delivering more concentrated energy. Meanwhile, the southern hemisphere is tilted away experiencing winter. 6 months later, the roles reverse. This shifting sunlight pattern changes temperature distributions across the globe, which affects wind patterns, storm tracks, and the very behavior of the oceans. Speaking of oceans, those vast blue basins covering over 70% of the Earth's surface aren't just passive players. They're the ultimate climate regulators. They absorb huge amounts of solar energy and store it like thermal batteries. Water takes longer to heat up than land, but it also cools down more slowly. This difference in heating and cooling between land and sea is one reason coastal regions have milder climates. It's why the air in a city like Boston might feel so much colder than the air in a seaside town in California during the winter, even if they're at the same latitude. Oceans also move in giant currents like the Gulf Stream or the Kuroshio Current, transporting warm water across great distances. These currents help to circulate heat from the tropics toward the poles, acting as a kind of atmospheric radiator. And when ocean conditions shift significantly, like during El Niño or La Niña events, they can have global ripple effects on rainfall droughts and temperatures, proving that the world's oceans have an enormous amount to say about the weather you experience. So to recap, without ever needing to get out of your cozy spot, you've now floated through the complex choreography of Earth's weather engine. The sun heats the planet unevenly, which causes air to rise and fall. The spinning Earth deflects this air into graceful curves. Jet streams carry it across the sky like high-speed ribbons, and the tilt of our planet ensures that no part of the Earth ever stays exactly the same for long. The result is a planet where no 2 days are ever truly alike, where the wind you feel on your cheek, the clouds drifting lazily above, and even the pattern of rain on your window are all part of a grand planetary ballet powered by sunlight and shaped by motion. It's a delicate balance, one that's been playing out for billions of years, and all of it, from the smallest breeze to the fiercest storm, begins with the sun's warm and distant touch. The energy that started its journey, now 93 million miles away, arrives here to create a continuous quest for equilibrium. And just as you are settling in, the same forces that brought you here are at work all around you, even in this quiet moment. A single photon of light, a simple molecule of air, and a planet spinning through the vastness of space. What is truly elegant is that this whole swirling, ever-changing system runs without a single switch or command. It is self-organizing, driven by the elegant poetry of physics. Gravity holds it close, sunlight stirs it, and the golden rule of thermodynamics ensures that energy will always try to spread out heat. Wants to move from hot places to cold ones, and pressure wants to equalize. The atmosphere rarely achieves perfect balance, of course, but it never stops trying. It's like your brain trying to find that perfect quiet thought before sleep. It doesn't always get there, but the attempt itself is the point. And that attempt is weather. So close your eyes if you like. Let the thought of this vast interconnected system wash over you. There's no need to analyze it, no need to understand every single detail. Just feel the gentle, invisible hand of these forces at work. The air moving from high pressure to low, the clouds forming in the sky, and all the quiet, ceaseless energy flowing all around you. You are part of it, and it is part of you, a constant exchange of energy and breath. Just as you feel the quiet stillness of your own body, the atmosphere is never truly still. It is a world of movement, of invisible sculptors constantly reshaping the air around us. You can't see it, but you can feel it dancing through your hair, pushing leaves across sidewalks, and occasionally flipping your umbrella inside out, just to remind you who's in charge. It's gentle and wild, playful and destructive, and yet it's really just air on the move. At its most basic level, wind is caused by differences in air pressure. That's it. When one region has higher atmospheric pressure than another, the air moves from the high-pressure area toward the low-pressure area to balance things out. The greater the difference in pressure, the stronger the wind. It's nature's version of tidying up, although the results are not always tidy. Think of pressure differences like hills and valleys. Air like water flows downhill from high pressure to low pressure. But unlike water, air doesn't move in straight lines thanks to the rotation of the Earth. This is where our friend the Coriolis effect comes back into play, gently nudging the moving air, deflecting it to the right in the northern hemisphere and to the left in the southern hemisphere. This twisting force gives wind its characteristic curves and helps shape the global wind patterns we observed from our high-altitude journey. Let's start at the planetary scale once more. We already touched on the trade winds and westerlies, but let's consider their role from a human perspective. Early civilizations, lacking modern instruments, had an intuitive understanding of these invisible forces. A historical fact is that ancient mariners in the Arabian Sea relied on the seasonal monsoon winds to travel between Africa and India for trade. This was a form of long-range weather forecasting based on pure observation and historical knowledge, a trust in the rhythm of the globe. This was not just a convenience. It was a matter of survival and commerce, the very lifeblood of their societies. Historians still debate whether these cultures had a purely empirical understanding of the patterns, or if their knowledge was deeply intertwined with religious and spiritual beliefs about the will of the gods. But either way, they listened to the wind, and the wind spoke of distant lands and opportunities. But wind isn't just a global phenomenon. It's also deeply local. In fact, some of the most fascinating winds occur on small scales, shaped by mountains, valleys, and coastlines. Take sea breezes, for example. On a sunny day, land heats up more quickly than water. The warm air above the land rises, creating a low-pressure zone. Cooler air from over the ocean rushes in to replace it, creating a gentle breeze that flows from the sea to the land. At night, the process reverses. The land cools faster than the sea, and now the breeze flows from land to sea. This rhythmic exchange is one of nature's simplest wind patterns and one of its most soothing. It's like the planet breathing in and out, a slow, steady pulse that you can feel on your skin. In mountainous regions, wind takes on even more dramatic forms. During the day, air near mountain slopes heats up and rises, drawing cooler air up from the valley in what's called an anabatic wind. At night, the air cools and becomes denser, flowing back down into the valley as a katabatic wind. These daily ups and downs can create dramatic temperature swings, and if you live in a mountain town, they're just part of life. Some katabatic winds are famous in their own right. The Mistral in southern France is a cold, dry wind that blows down the Rhone Valley toward the Mediterranean. It can be fierce, sometimes exceeding 50 miles per hour, and is known for its role in shaping the region's climate and even influencing local architecture. Many homes are built with small sheltered windows facing away from its path. In California, there are the Santa Ana winds, which blow from the desert toward the coast during certain times of the year. These winds are hot and dry and can exacerbate wildfires by fanning flames and drying out vegetation. Their arrival is often met with a mix of awe and dread, a reminder that wind, for all its elegance, can also be a harbinger of danger. One of the most extraordinary wind systems in the world is the Chinook wind, often called a snow eater. Chinooks occur on the eastern slopes of the Rocky Mountains when warm, dry air descends from the mountains into the plains. These winds can cause temperatures to rise dramatically in just a few minutes, by as much as 40 degrees Fahrenheit in less than an hour. Imagine stepping outside into a winter morning, only to be able to peel off your coat by lunchtime. It's a bit like nature turning on a giant hairdryer. Wind can also be sneaky. Some gusts are sudden and unexpected, like microbursts, which are powerful downdrafts that occur during thunderstorms. These bursts of wind descend rapidly from the cloud and spread out on the ground, causing damage that can mimic a tornado. Microbursts have been known to knock over trees, damage buildings, and even pose serious hazards to aircraft. And then there are dust devils, mini whirlwinds, that form on hot, dry days when the ground heats unevenly. These are not tornadoes, though they look like tiny twirling versions. Dust devils are usually harmless spinning a column of air and debris just a few feet wide and a few dozen feet high. They're common in deserts and can make for a funny, if slightly mischievous sight. At the other end of the spectrum, we have gales and cyclones, large-scale wind systems associated with intense, low-pressure areas. A gale is generally defined as sustained winds of over 39 miles per hour, strong enough to bend trees and make walking difficult. Cyclones, depending on where they occur and how strong they are, can bring hurricane-force winds, torrential rain, and massive storm surges. But not all winds are violent or even noticeable. Some are persistent background players, like the jet streams we talked about high above the Earth's surface. These fast-moving ribbons of air located around the tropopause can steer weather systems and influence everything from airplane flight times to seasonal temperature trends. They travel at speeds of 100 to 200 miles per hour, flowing from west to east and meandering like lazy rivers in the sky. A quirky detail about wind is that it's not just about movement, it's about sound. The way wind travels and interacts with a landscape creates unique noises. It's the reason a forest sounds different in a gentle breeze than in a gusty wind. It's the reason you hear a quiet, steady hiss over open water, but a low, mournful moan when the wind blows across telephone wires. This acoustic quality is a form of communication, a whisper from the atmosphere that tells you about its speed and its surroundings, without you ever having to see a single thing. Throughout history, humans have both respected and relied on wind. Farmers have watched it for signs of changing weather. Windmills were invented in Persia as early as the 9th century to grind grain and pump water, a testament to our long-standing desire to harness this power. And today, we harness it for renewable energy, capturing its power to turn giant blades and generate electricity without burning a drop of fuel. Historians still debate the true origin of the windmill and whether the concept was developed independently in different regions or spread from a single source. Wind also plays a subtle but important role in temperature regulation. It carries warm air away from hot places and brings cool air into warm ones. On a hot day, a breeze can feel like a lifeline. On a cold one, it can bite straight through your coat. This is where the concept of wind chill comes in, a measure of how cold it feels when wind removes heat from your skin. It doesn't actually lower the temperature, but it sure feels like it. It's a reminder that wind isn't just a summer breeze, it can be a winter bite. And while wind may seem chaotic, it's governed by precise laws of physics. It follows the paths laid out by pressure gradients influenced by topography, temperature, and the spinning earth. Whether it's a gentle rustling of leaves or the howl of a winter storm wind is a language the planet speaks every day. So next time you hear the trees swaying outside your window or feel a breeze graze your cheek, take a moment to appreciate the silent, swirling presence of wind. It's a constant companion, always moving, always reshaping the air around us, and though we can't see it, wind is one of the clearest signs that the atmosphere is alive in motion and full of quiet power. Now, as you float in this gentle air, let's talk about the sky's most silent and artistic architect, water. Moisture in the air is one of those things you don't usually notice until it's either making your hair misbehave or fogging up your glasses. But the truth is, the invisible water drifting through the atmosphere plays a central role in shaping weather across the planet. It creates clouds, causes rain and snow, and fuels storms. It's also responsible for some of the most beautiful and dramatic scenes in the sky. In short, moisture is the atmosphere's secret ingredient, and it's everywhere, even when the skies look perfectly clear. Let's begin with humidity, which is just a fancy word for water vapor in the air. Water vapor is water in its gas form, and the air can hold more or less of it depending on the temperature. Warm air can hold more water vapor, while cold air can hold less. This is why summer days can feel so muggy and tropical, while winter air often feels crisp and dry. It's not just your imagination. There really is less moisture floating around in the cold. A historical fact about this is that for centuries, people would use simple hygrometers instruments made of things like twisted strings of human hair to measure humidity, a testament to how long we have been trying to quantify this invisible part of our world. When meteorologists talk about humidity, they usually mention two things: absolute humidity and relative humidity. Absolute humidity refers to the actual amount of water vapor in the air, like saying there are 12 grams of water per cubic meter. Relative humidity, on the other hand, is a bit more emotional. It's a percentage that compares how much water vapor is in the air to how much the air could hold at that temperature. So, if the relative humidity is 100%, the air is completely saturated. It can't hold any more moisture, and condensation is likely. That's when you start to see dew fog or clouds forming. You've probably experienced this yourself on a hot summer day. Even if the air isn't saturated high, relative humidity can make everything feel sticky and sluggish. That's because your sweat doesn't evaporate as easily in humid air, which is your body's natural way of cooling down. In contrast, dry air lets sweat evaporate quickly, leaving you feeling cooler, though possibly more like a desert lizard than a tropical bird. Now let's talk about clouds. These soft, fluffy sky blankets may look light and airy, but they are actually made up of countless tiny water droplets or ice crystals, depending on the temperature. Each droplet is so small, it takes about 1 million of them to make a single raindrop. Despite their delicate appearance, an average cumulus cloud, a big puffy one like you might draw as a child, can weigh hundreds of thousands of pounds. That's right. A cloud can be as heavy as a jumbo jet, just floating up there, as if gravity has taken the day off. This is a quirky, wonderful truth of physics that reminds us that density is far more important than mass when it comes to floating. But how do these clouds form in the first place? It all begins with evaporation. Water from oceans, lakes, rivers, and even moist soil gets heated by the sun and turns into water vapor. That vapor rises into the atmosphere because warm air is less dense and more buoyant than cold air. As the vapor ascends, the air pressure drops and the air expands, which makes it cool down. Cooler air can't hold as much water vapor, so the excess vapor condenses into tiny droplets or ice crystals. But here is the most poetic part of the process. This condensation doesn't happen out of thin air. It needs a particle to cling to. These microscopic particles, like dust, salt, or pollen, are known as cloud condensation nuclei. They are the tiny invisible seeds that allow water to collect and form visible clouds. They are the little secrets the atmosphere keeps, and they are everywhere from the Sahara Desert to your own backyard. It's a beautiful thought that the clouds above you might be seeded by a speck of pollen from a flower miles away. Different cloud types form, depending on how the air rises and how much moisture is available. If the air rises gently, you get stratus clouds, flat gray, and often responsible for that overcast gloom that feels like it's sitting on your shoulders. When the air rises quickly, it can form cumulus clouds, those fluffy cotton balls of the sky. If conditions are unstable and very moist, those cumulus clouds can grow and grow into towering cumulonimbus clouds, which are the giants of the cloud world and the engines behind thunderstorms. There are many other types of clouds too. Cirrus clouds are high-altitude wisps made mostly of ice crystals. They often look like feathers and can signal an approaching weather front. Lenticular clouds form over mountains and look like flying saucers, a testament to the influence of geography on atmospheric flow. The mammatus clouds hang down like pouches and often appear during dramatic weather events. There's even a type called altocumulus castellanus that looks like a row of little turrets marching across the sky. The names might sound like Harry Potter spells, but they're all part of a very real atmospheric lexicon. Once a cloud forms, it doesn't necessarily rain right away. A cloud needs to grow droplets big enough to overcome the pull of air resistance and start falling. This happens through a process called coalescence, where droplets bump into each other and merge into larger ones. When they become heavy enough, typically about 2 millimeters in diameter, they fall to the ground as raindrops. In very cold clouds, the process might involve ice crystals instead, with moisture freezing around them until they become heavy enough to fall as snow. Interestingly, raindrops don't look like teardrops, despite what every cartoon ever might suggest. As they fall, they're shaped more like hamburger buns flattened on the bottom by air resistance. If a drop gets too big, it can split into smaller droplets on the way down. So now as you lay here with your own world, seeming so still, remember that the atmosphere is a canvas and moisture is its paint. It is a constant quiet work of art, a perpetual process of evaporation, condensation, and transformation. It is the story of water rising and falling forever in motion. And just as the clouds shift and change, so too do the thoughts in your mind. Let them drift. Let them float. There is no need to hold on to a single one. Just observe them like you would a cloud passing slowly by in the sky. The history of cloud classification is a fascinating one. It's a relatively recent science dating back to the early 19th century when an amateur meteorologist named Luke Howard proposed the Latin-based system we still use today. Before Howard, clouds were often described with poetic but imprecise terms. He was the first to give them names that described their form and altitude, allowing scientists to speak a common language about the sky. Historians still debate whether Howard was more of a scientist or a romantic, as his work was so beautifully rooted in both observation and poetry. And yet this simple act of naming gave us a way to organize the chaos of the sky, to find order in the ever-changing shapes above. In a way, understanding the clouds is like learning to read the quiet language of the sky. Each type has something to say about the conditions that created it and what might be coming next. A high, feathery cirrus cloud might whisper of a coming change, while a dark, low-lying stratus cloud will silently promise an overcast day. They are not random puffs of white. They are the visible tips of an invisible process, a delicate balancing act of temperature, moisture, and motion taking place all around you. Every droplet in the air, every wisp of mist, every sudden shower, they're all part of this vast, elegant water dance happening above our heads. And all of it begins with moisture in the air, unseen, often unnoticed, but endlessly vital. Now that you understand how a cloud is formed, let's talk about what happens next. A cloud doesn't necessarily rain right away. A cloud needs to grow droplets big enough to overcome the pull of air resistance and start falling. This happens through a process called coalescence, where droplets bump into each other and merge into larger ones. When they become heavy enough, typically about 2 millimeters in diameter, they fall to the ground as raindrops. In very cold clouds, the process might involve ice crystals instead, with moisture freezing around them, until they become heavy enough to fall as snow. Interestingly, raindrops don't look like teardrops, despite what every cartoon ever might suggest. As they fall, they're shaped more like hamburger buns flattened on the bottom by air resistance. If a drop gets too big, it can split into smaller droplets on the way down. But rain is just one form of the atmosphere's tears. When temperatures are below freezing all the way from the cloud to the ground, you get snow. A snowflake starts its life high in the atmosphere as a tiny dust particle. Water vapor in the air condenses directly onto this speck and freezes, forming an ice crystal. As the crystal floats through the cloud, more water vapor continues to condense and freeze onto it, causing it to grow. The shape of the snowflake depends on temperature and humidity, which change constantly as the flake falls. That's why no two snowflakes are exactly alike, or at least the chances of finding two identical ones are extremely low. Most snowflakes form the classic six-arm shape, a hexagon. This is because of the molecular structure of water. Each molecule of H2O tends to bond at a specific angle, forming symmetrical repeating patterns. Some flakes look like plates, others like needles or stars. Under a microscope, they reveal breathtaking geometric detail, all sculpted by nothing more than temperature and air moisture. Snow is light, but it adds up fast. A single cubic foot of fresh fluffy snow can weigh between 5 and 15 pounds, depending on moisture content. When millions of flakes fall over an area, it's easy to see how a gentle snowstorm can quickly turn into a heavy burden on rooftops and tree branches. Wet snow with its higher water content is denser and heavier than the dry, powdery kind favored by skiers. Now, not all frozen precipitation is quite as elegant. Sleet occurs when snowflakes begin to fall from high cold clouds, but pass through a layer of warmer air on the way down. In that warm layer, they partially melt, becoming little droplets. Then, as they descend further and pass into a colder layer closer to the ground, they refreeze into tiny pellets of ice before hitting the surface. These pellets bounce when they land and often create a crunchy layer that's slippery underfoot, but still manageable. Freezing rain, however, is a trickier customer. Like sleet. Freezing rain begins as snow high in the atmosphere. It melts completely into rain as it falls through a warm layer of air. But then, it enters a shallow layer of cold air just above the ground. The air near the surface is below freezing, but the rain doesn't have time to refreeze while it's falling. Instead, it stays liquid, what we call supercooled, until it hits the surface. The moment it touches something like a sidewalk, a car, or a tree branch, it freezes instantly, forming a thin, slick coating of ice. This glaze of ice is beautiful in a dangerous kind of way. It can make every twig glisten like crystal, and every road a hazard. Unlike snow, which can be shoveled or plowed with relative ease, ice clings to everything and makes walking or driving extremely treacherous. Freezing rain is a major cause of power outages in winter, as ice adds weight to power lines and tree limbs, often snapping them. Then there's hail, which is not just frozen rain, but something altogether different. Hail forms in strong thunderstorms with powerful updrafts. A small ice pellet forms high in the cloud and gets tossed around by the rising air, collecting layers of supercooled water that freeze on contact. Each time the hailstone gets lifted and dropped again, it gains more icy layers, growing bigger and heavier, until it finally becomes too heavy to stay aloft. Hailstones can range from the size of peas to the size of grapefruits, though the latter is thankfully rare. Still, if you ever hear of hail the size of golf balls, it's not just a poetic exaggeration. It happens, and it's best experienced from indoors. But precipitation doesn't always need to fall from the sky to show off. Sometimes it simply condenses on surfaces as dew. Those sparkling droplets you might see coating grass on a cool morning form when the ground radiates heat overnight and cools down, allowing moisture in the air to condense. If the temperature drops below freezing, the dew turns into frost, which decorates leaves and windows with intricate patterns of ice. A quirky, little-known detail about frost is that it doesn't fall from the sky. It grows in place like a delicate atmospheric sculpture. In certain conditions, winter can also bring ice fog. This occurs when tiny droplets of supercooled water in the air freeze into minuscule ice crystals near the ground, creating a dense, frozen mist. Ice fog is common in extremely cold places like Alaska or northern Canada, where temperatures often fall below 20 degrees Celsius. It gives the air a silvery glow and can reduce visibility dramatically, just like regular fog, only with a sparkling frozen edge. A common historical fact is that in many ancient cultures, the first snowfall of the season was seen as a sacred event, an act of purification, or a signal from the gods. In places like ancient Japan, snowfall was an object of reverence and artistic inspiration, with poets writing about its quiet, transformative power. This reverence for snow and its ability to turn the familiar world into a hushed, uniform landscape speaks to a deep human connection with weather as something more than just a scientific phenomenon. Historians still debate whether this reverence was born purely out of aesthetic appreciation, or if it was more directly linked to the practical importance of snowpack as a source of water for irrigation and drinking in the spring. It's all part of a single continuous story. Water evaporates from oceans and lakes, rises into the air forms. Clouds falls as rain or snow and flows back into rivers and seas to start the journey all over again. This water cycle has been running for billions of years and is essential to every form of life on the planet. And just like that water cycle, the thoughts in your mind are in a constant state of flow. They rise and fall. They gather and dissipate. They can be as light as a snowflake or as heavy as a downpour. There is no need to hold on to any of them. Just let them go. Let them fall away and find the quiet, calm space in between. Sometimes the atmosphere decides to throw a party. And when it does, thunderstorms are its version of fireworks. They rumble, flash pour, and sometimes even toss hail the size of walnuts at your roof. Yet for all their drama, thunderstorms are simply a product of air, water, and a touch of electrical flair, like a weather cocktail with a very loud garnish. Let's begin with how they form. At the heart of every thunderstorm is something very basic: warm, moist air rising into cooler air above. This rising air is called an updraft, and it's usually set in motion by surface heating. Picture a hot summer afternoon in, say, Oklahoma. The sun has been baking the ground all day, and now a pocket of air near the surface gets warmer than the air around it. Because warm air is lighter, it begins to rise. As it ascends, it cools. Remember, air expands and loses heat as it rises into lower pressure. If that air contains enough moisture, it will eventually reach its dew point. The temperature at which the water vapor it carries condenses into liquid droplets. This process releases heat, known as latent heat, which gives the air another boost upward. It's like strapping little rockets to an already rising balloon, a self-reinforcing engine of motion. As this continues, a cloud begins to grow. At first, it may just look like an innocent, fluffy cumulus cloud, but with enough moisture and instability, it can grow into a towering cumulonimbus cloud, a vertical beast that can stretch up to 10 miles into the sky. That's higher than Mount Everest, and then some. Inside, the cloud chaos is brewing. The updraft keeps shoving warm, moist air higher and higher, while gravity pulls the cooled air and falling precipitation down in what's known as a downdraft. This up and down motion is what drives the engine of a thunderstorm. When the updraft and downdraft become organized and strong, the storm is officially underway. Thunderstorms are classified into 3 stages: the cumulus stage, the mature stage, and the dissipating stage. In the cumulus stage, warm air rises and forms a cloud. It's a bit like blowing up a balloon, steady and fairly quiet. Then comes the mature stage, which is when things get noisy. The cloud grows vertically, raindrops start to form and fall. Lightning begins to flicker, and thunder makes its debut. This is the stage where updrafts and downdrafts coexist in a swirling dance of moisture and motion. Finally, in the dissipating stage, the downdraft takes over. The falling rain cools the surface, cutting off the warm air supply that was feeding the storm. With no more rising fuel, the storm slowly collapses and fades away. But let's not skip over the dramatic centerpiece of any thunderstorm: lightning. Lightning is quite simply nature's way of balancing electrical charges, though it certainly does so with flair. As the storm churns, tiny ice crystals and water droplets inside the cloud bump into each other and become electrically charged. The lighter ice particles tend to pick up positive charges and are carried to the top of the cloud. Heavier hail and water drops become negatively charged and sink to the bottom. This separation of charge creates an enormous voltage difference, millions of volts, between different parts of the cloud, between the cloud and the ground, or even between clouds. Eventually, the air can't resist anymore and a discharge occurs. That's lightning. The process begins with a stepped leader, a faint, invisible path of charged particles that zigzags downward from the cloud. When it gets close to the ground, the electric field becomes so intense that the ground sends up a streamer to meet it. When they connect, a powerful current surges through the channel, creating a brilliant flash of light. That's what we see as lightning. The air in the lightning channel is heated to around 50,000 degrees Celsius in just a few microseconds. That's 5 times hotter than the surface of the sun. The sudden heating causes the air to expand explosively, creating a shock wave that we hear as thunder. Because light travels so much faster than sound, you always see the lightning before you hear the thunder. If you want to estimate how far away a lightning strike is, you can count the seconds between the flash and the rumble. Divide that number by 5, and you'll have the distance in miles. So if you count 10 seconds between the flash and the thunder, the strike was about 2 miles away. Lightning comes in many flavors. There's cloud-to-ground lightning, which is the most dramatic and dangerous kind, especially if you happen to be holding a golf club in an open field. There's intracloud lightning, which dances around inside a single cloud. And there's cloud-to-cloud lightning, which leaps between separate storm clouds, like some kind of atmospheric daredevil. Then there are the more exotic types, like ball lightning, which appears as glowing orbs and remains a bit of a mystery, and sprites and blue jets, which are high-altitude electrical phenomena that shoot upward into the mesosphere. Sprites look like red jellyfish and often appear above large thunderstorm systems. They were once dismissed as pilots' hallucinations, but we now know they're very real and quite spectacular. A historical fact is that one of the first people to study lightning in a scientific way was Benjamin Franklin in the 18th century. His famous kite experiment in a thunderstorm, a dangerous and audacious act, proved that lightning was a form of electricity. This discovery was a monumental leap forward in our understanding of the natural world and led to the invention of the lightning rod, a device that has protected countless buildings from the destructive power of a lightning strike. This was a transition from seeing lightning as an act of divine fury to seeing it as a force of nature that could be understood and managed. A quiet fact that is often overlooked is that while his experiment is famous, Franklin himself never wrote a detailed account of it, and much of what we know about it comes from the writings of others. This has led to an interesting academic debate about the exact details of his experiment and what he was truly trying to prove. A single lightning bolt can carry over 1 billion joules of energy, enough to power a small town for a brief moment. It can cause wildfires, damage buildings, and sadly, can be deadly. That's why safety experts say, when thunder roars, go indoors. It may not rhyme perfectly, but it's good advice. Thunderstorms also bring another dramatic feature: hail. As we mentioned in the last chapter, hail forms in the strong updrafts of a thunderstorm. Water droplets are carried high into the storm freeze and then fall only to be picked up again and coated with more water that freezes. Each loop adds another layer, like a snowball getting rolled across a field. Eventually, the hailstone becomes too heavy for the updraft to hold, and down it comes. Depending on the storm's strength, hailstones can be as small as peas or as large as softballs. And then there's wind. Thunderstorms often produce strong gusty winds as the downdrafts push air toward the ground. These winds can spread out rapidly once they hit the surface, causing what's known as a downburst. Downbursts can be very destructive, sometimes mistaken for tornadoes, though they behave quite differently. Speaking of tornadoes, yes, some thunderstorms do spawn them, but not all thunderstorms are created equal. The ones that produce tornadoes are usually part of a special category called supercells. A supercell is a type of thunderstorm with a rotating updraft known as a mesocyclone. This rotation is caused by wind shear changes in wind speed and direction with height, which creates a horizontal spinning effect in the atmosphere. If this horizontal spin gets tilted into a vertical orientation by a strong updraft, it can begin rotating around a vertical axis. Under the right conditions, a rotating funnel cloud can descend from the base of the storm. If it touches the ground, it becomes a tornado. These events are rare, and the conditions have to be just right, but when they do occur, they're among the most powerful and violent weather phenomena on Earth. Still, most thunderstorms are more modest affairs. Short-lived bursts of energy that bring rain wind and the occasional bolt from the blue. They can form in clusters known as multi-cell storms or along weather fronts, especially cold fronts, where advancing cool air lifts warm, moist air up into the sky. One interesting phenomenon tied to thunderstorms is the gust front. This is the leading edge of cool air being pushed out by a storm's downdraft. As this air spreads out, it lifts the warm air ahead of it, which can create new storm cells in a chain reaction. In this way, one thunderstorm can give birth to another, like a weather-based game of tag. Despite all the noise and drama, thunderstorms are surprisingly common. At any given moment, there are roughly 2,000 thunderstorms happening on Earth. That's right. While you're lying in your quiet space somewhere on the planet, clouds are flashing and grumbling their way across the sky. They're a reminder of how dynamic and alive our atmosphere really is. Each storm is a brief but powerful expression of nature's energy, a temporary disturbance in the atmosphere's endless quest for balance. And when the sky lights up with a sudden flash and follows with a deep rolling growl, it's not just noise. It's the sound of the sky releasing tension, one electric exhale at a time. When the atmosphere really wants to make a statement, when it's had enough of polite breezes and scattered showers, it unleashes its most dramatic spectacles: tornadoes and hurricanes. These mighty tempests are the headline acts in Earth's meteorological theater. Swirling masses of raw energy that can carve paths through landscapes and rewrite coastlines. They're loud, powerful, and sometimes terrifying. But beneath the fury, they follow the same fundamental principles that guide all weather: air, moisture, pressure, and motion, just turned up to 11. Let's begin with tornadoes. Tornadoes are rotating columns of air that stretch from the base of a thunderstorm down to the ground. They're short-lived compared to hurricanes, often lasting only a few minutes, but they can be astonishingly intense. In fact, they hold the record for the strongest surface winds ever measured on Earth. The most powerful tornadoes can reach speeds over 300 miles per hour. That's faster than a Formula One car and considerably less polite. Tornado formation is still not fully understood, but meteorologists have identified a few key ingredients. First, you need a very strong thunderstorm, usually a supercell, the same kind of storm we touched on in the previous chapter. Supercells are special because they have a rotating updraft called a mesocyclone, which is a spinning column of air within the storm itself. This rotation begins with wind shear, which means that winds at different altitudes are blowing at different speeds or directions. Imagine surface winds coming from the southeast, while higher winds are coming from the west and moving faster. This creates a horizontal rolling motion in the lower atmosphere. If a thunderstorm forms above this zone of rolling air, the storm's powerful updraft can tilt that rotation vertically. The result? A slowly spinning column of air stretching upward through the storm. But not every mesocyclone becomes a tornado. For that to happen, the rotation must tighten and stretch downward, forming a funnel cloud. If that funnel touches the ground, it becomes a tornado. The process is delicate and depends on subtle changes in air pressure, moisture, and terrain. Some storms flirt with tornado formation for hours and never produce one. Others drop a twister with little warning. Once formed, a tornado can travel at speeds ranging from just a few miles per hour to more than 70. Most are small and relatively weak, classified as EF0 or EF1 on the enhanced Fujita scale. But occasionally, a monster emerges, an EF4 or EF5 tornado capable of flattening entire neighborhoods and throwing cars like paperweights. The enhanced Fujita scale ranks tornadoes from 0 to 5 based on the damage they cause. An EF0 might break tree branches and knock over signs. An EF5, the highest rating, tears homes from their foundations and leaves behind a trail of debris that looks more like a war zone than a weather event. Tornadoes are most common in the United States, particularly in a region known as Tornado Alley, which stretches across the Central Plains from Texas up through Oklahoma, Kansas, Nebraska, and parts of South Dakota. The geography here is perfect for tornado formation. Warm, moist air from the Gulf of Mexico meets cold, dry air from the Rockies in Canada, all under a wide open sky. But tornadoes can and do happen elsewhere. They've been recorded on every continent except Antarctica. Waterspouts tornadoes that form over water can be found off the coasts of Florida and in the Mediterranean. Even the United Kingdom, not known for its extreme weather, sees several tornadoes each year, though they tend to be mild and rather polite by comparison. Now let's shift our attention to the larger, longer-lasting, and much more predictable cousin of the tornado, the hurricane. Hurricanes, known in different parts of the world as cyclones or typhoons, are massive rotating storm systems that form over warm ocean waters. They can be hundreds of miles wide and last for days or even weeks. While tornadoes are small, violent dancers, hurricanes are enormous, slow-moving engines of atmospheric energy. For a hurricane to form, several conditions must be met. First, you need warm ocean water at least 70 centimeters while extending to a depth of around 150 feet. This warm water provides the fuel for the storm. Second, you need a pre-existing disturbance in the atmosphere, such as a cluster of thunderstorms. Third, you need low vertical wind shear, meaning the winds at different altitudes aren't varying too dramatically. Too much wind shear can rip a developing storm apart before it gets started. When these ingredients come together, the warm ocean water begins to evaporate, adding moisture to the air. As the moist air rises, it cools and condenses, forming clouds and releasing latent heat, the same sneaky energy release we discussed in thunderstorm formation. This heat warms the air around it, causing it to rise even more. As air continues to rise and spiral inward due to the Coriolis effect, a low-pressure center forms and a tropical depression is born. If the storm continues to intensify, organizing its circulation and drawing in more moisture, it becomes a tropical storm. Once sustained winds reach 74 mph, it earns the title of hurricane. A historical fact is that the practice of naming tropical storms with human names began in the early 20th century to make them easier to track and remember, a simple solution to a complex problem. Historians still debate the ethical implications of this practice, as it can sometimes trivialize the destructive power of these storms. A hurricane has several distinct parts. At the center is the eye, a calm, clear region of low pressure, where winds are light and the sky may even be blue. Surrounding the eye is the eye wall, a ring of towering thunderstorms that contains the storm's strongest winds and heaviest rain. This is the most dangerous part of the storm. Beyond the eye wall are rain bands, spiraling bands of showers and storms that extend outward for hundreds of miles. Hurricanes are ranked on the Saffir-Simpson hurricane wind scale, which classifies them from Category 1 to Category 5 based on sustained wind speeds. A Category 1 hurricane has winds between 74 and 95 mph, enough to cause damage to roofs, trees, and power lines. A Category 5 hurricane with winds exceeding 157 mph can cause catastrophic destruction, rendering areas uninhabitable for weeks or months. But wind isn't the only danger. Hurricanes also bring storm surge, a rise in sea level caused by the storm's winds pushing water toward the shore. Storm surge is often the deadliest aspect of a hurricane, particularly in low-lying coastal areas. Combined with heavy rain, it can cause widespread flooding, sweeping away homes and infrastructure. And then there's the rain. Hurricanes can dump more than 2 feet of rain over just a few days, leading to flash floods and landslides far inland. The sheer size and slow movement of some hurricanes mean that even areas not directly in the path of the eye wall can experience days of torrential rain and strong winds. Interestingly, hurricanes serve an important function in Earth's climate system. They help redistribute heat from the tropics toward the poles, moving excess thermal energy away from the equator. In a strange and violent way, hurricanes are part of the atmosphere's endless quest for balance. A quirky detail is that hurricanes don't last forever. Once a hurricane moves over cooler water or land, it begins to weaken, cut off from its warm water fuel source. The storm's engine sputters, its winds die down, and its rains slowly taper off. Despite their power, both tornadoes and hurricanes are expressions of the same fundamental principles that govern all weather. They're symptoms of imbalance of heat, needing to move of pressure seeking equilibrium. In that sense, they're not freak events, but entirely natural outcomes of the forces that keep Earth's atmosphere alive and in motion. They are a reminder that the world is always in a state of flux, always seeking balance, sometimes with a quiet whisper, and sometimes with a mighty roar. As you settle into your quiet space, let the image of this immense power, this great atmospheric engine, simply pass by. Sometimes weather doesn't arrive with drama. There's no thunder, no lightning, no swirling snow. Instead, it chooses to enchant rather than overwhelm. These are the gentle wonders of the atmosphere, the optical illusions and subtle spectacles that remind us the sky is at its heart an artist. It's in the quiet aftermath of a storm, or when sunlight meets moisture in just the right way, that the most beautiful things can happen. Let's start with the most iconic of all, the rainbow. A rainbow isn't an object you can touch or travel to. It's an optical and meteorological phenomenon, essentially a trick of light and perspective. When sunlight passes through a raindrop, it gets bent or refracted. Then it reflects off the back of the drop and is bent again as it exits. This bending and bouncing causes the light to split into its component colors: red, orange, yellow-green, blue, indigo, and violet. Each color bends slightly differently, with red refracting the least and violet the most. The result is a circle of color, although we usually only see a semicircle or an arc because the ground gets in the way of the full shape. The angle of a primary rainbow is always about 42 degrees from the direction opposite the sun. This means the sun has to be behind you, and rain or mist has to be in front of you. A quirky detail is that you can never actually reach the rainbow. It moves with you. You're not even seeing the same rainbow as someone a few feet away. Each viewer sees a slightly different version built from the light entering their eyes alone. It's as personal as a fingerprint, but made of light. Sometimes you'll see a double rainbow, with a second, fainter arc outside the first. This occurs when the light reflects twice inside the raindrop before exiting. Because of the extra reflection, the secondary rainbow appears higher in the sky and has its colors reversed: red on the bottom and violet on top. A historical fact is that the phenomenon of the double rainbow was understood by the ancient Greek philosopher Alexander of Aphrodisias, who accurately described the different angles of the two arcs. Between the two arcs, there's often a darker band called Alexander's band, named after him. It's a subtle but beautiful piece of evidence that our atmosphere is always doing the same physics it has for millennia. Historians still debate whether other early cultures had a similar scientific understanding of this phenomenon, or if they simply saw it as a purely mythical divine message. Now what happens if the sunlight interacts with something other than rain? Enter halos, sundogs, and pillars of light. Atmospheric optics formed not by raindrops, but by ice crystals in high-altitude clouds. These crystals are usually found in cirrostratus clouds, which form 5 to 8 miles above the Earth's surface. A halo is a bright circle, often with a subtle rainbow edge, that forms around the sun or the moon. It happens when sunlight or moonlight passes through hexagon-shaped ice crystals that bend the light at an angle of 22 degrees. The result is a ghostly ring that seems to float around the sun like a celestial crown. Halos can appear in any season, but they're especially common in cold weather when the upper atmosphere is rich with ice. Sundogs, also known by their more poetic name, parhelia, are bright spots that appear on either side of the sun, often within a halo. They look like small, colorful duplicates of the sun and can be surprisingly vivid, especially when the sun is low in the sky. Like halos, sundogs are caused by ice crystals, but the crystals must be oriented just right, like tiny floating mirrors. Then there are light pillars, vertical beams of light, that appear to shoot straight up from the sun or even from street lamps. These are caused by flat plate ice crystals slowly falling through the air and reflecting light in a column. They look otherworldly, like something out of a science fiction film, but they require no aliens, just a calm atmosphere and the right kind of ice. Another lesser-known gem is the glory. Despite its grand name, a glory is delicate and subtle. It appears as a series of colored rings, much like a miniature rainbow, that form around the shadow of your head when it's cast onto a cloud or fog bank. Glories are most often seen from airplanes when the aircraft casts a shadow on a cloud below, surrounded by shimmering rings of color. The effect is created by backscattered sunlight interacting with tiny droplets in the cloud. Pilots and passengers alike often refer to it as the glory of the pilot. Also related are coronas, which form when light diffracts around individual water droplets, creating tight, colorful rings around the sun or moon. Unlike halos, coronas are small and close to the bright object. They're often seen through thin clouds or mist and have a much more compact, pearlescent appearance. And then, of course, there's the sky's more flamboyant display, crepuscular rays, sometimes called God rays. These are beams of sunlight that appear to radiate from the sun, often during sunrise or sunset, when the sun is low and clouds scatter the light. The rays seem to fan out across the sky, but it's really just perspective at work, similar to how railroad tracks appear to converge in the distance. Crepuscular rays are caused by light streaming through gaps in clouds or mountains and illuminating particles in the air dust, moisture, even pollen. The light and shadow work together to create sharp contrast that our eyes interpret as rays of divine or magical light. One could almost say that a single puff of cloud is the universe's way of creating its own spotlights just for a moment. Now let's venture into the twilight for one more optical marvel, the green flash. This rare event occurs just before sunrise or just after sunset, when the sun is almost entirely below the horizon. For a second or two, the top edge of the sun can appear green. This happens because the atmosphere acts like a prism bending sunlight. Blue and green light bend more than red and orange, and under the right conditions, the very last sliver of sunlight may appear green. It's brief blink, and you'll miss it. But sailors and skywatchers have cherished sightings of the green flash for centuries. There's also lunar rainbows, or moonbows, which are exactly what they sound like. Rainbows formed by moonlight instead of sunlight. These are much fainter than regular rainbows because moonlight is so much weaker. You need just the right conditions, a full or nearly full moon, rain or mist in the air, and the moon positioned low in the sky behind you. Moonbows often appear white or silver, but if you look closely or photograph them with a long exposure, you might spot their pale colors. All of these phenomena are reminders that light and atmosphere are constantly playing together. We don't always notice the show, but when the conditions are right, the sky becomes a canvas for optical marvels, subtle or bold, fleeting or long-lasting. You don't need fancy equipment to see these wonders, just a bit of curiosity, a willingness to look up, and sometimes the patience to wait for the perfect combination of light, moisture, and timing. Whether it's a rainbow arching after a summer storm, a halo encircling a wintry sun, or a faint glory floating around your airplane shadow, each of these phenomena is a quiet whisper from the sky, reminding us that nature doesn't only work in thunder and lightning. It also speaks in color and shimmer in light, bending gently through air and water. The weather may shape the world, but light paints it. And every now and then, the atmosphere becomes not just a system, but a gallery. Weather can be intensely local. You might be enjoying sunshine while your friend a few miles away is sheltering from rain. But it's also wonderfully global. Around the world, weather varies wildly, depending on geography, latitude, ocean currents, and even elevation. From sticky monsoons to swirling sandstorms, each region has its own unique climate fingerprint. Let's take a slow and fascinating tour of how weather works around the world and how the same sky can behave so very differently from place to place, all from the comfort of your own quiet space. Let's begin with the monsoon, one of the most important and dramatic seasonal weather systems on the planet. The word monsoon comes from the Arabic mausim, meaning season, and it refers to a seasonal wind pattern that brings a major shift in precipitation. Most people associate monsoons with heavy rain, but a monsoon is really a large-scale wind reversal, driven by temperature differences between land and sea. Nowhere is the monsoon more powerful than in South Asia, particularly. India, Bangladesh, Nepal, and surrounding countries. In the summer, the land heats up faster than the ocean, creating a large area of low pressure over the Indian subcontinent. Moist air from the Indian Ocean rushes in to fill the void, rising as it hits the Himalayas and condensing into vast columns of rain. The result is weeks or even months of nearly non-stop precipitation. The monsoon is essential to life in the region. It waters crops, fills rivers, and recharges aquifers. But it can also bring dangerous floods, landslides, and disruptions to daily life. Still, it remains a welcome guest to millions, especially after the scorching dry heat of pre-monsoon summer. A historical fact is that ancient trade routes in the Indian Ocean were carefully planned around the monsoon, with merchants waiting months for the wind to shift to carry their ships to their destinations, a testament to how human civilization has long been shaped by these great seasonal breaths of the earth. Historians still debate the extent to which this reliance on predictable weather patterns fostered a more collective, community-oriented approach to life and trade in these regions. Further east, places like Thailand, Vietnam, and the Philippines also experience monsoon patterns, though the timing and strength vary. In East Asia, the East Asian monsoon brings hot, wet summers and cold, dry winters, heavily influencing agriculture and urban planning alike. Meanwhile, in northern Australia, a monsoon system brings tropical storms and torrential rain to the top end during the southern hemisphere's summer, usually from December to March. Locals call it the wet, and it's accompanied by stunning lightning displays and dramatic steamy skies. A quirky detail about monsoons is that they can sometimes be accompanied by an atmospheric phenomenon known as the monsoon trough, a low-pressure area that can sit for weeks, acting as a breeding ground for multiple storms. Now let's take a detour into the world of desert weather, a place where extremes are the norm. Deserts are often thought of as empty, lifeless spaces, but they are teeming with atmospheric action. In the Sahara, the world's largest hot desert, daytime temperatures can soar above 120-degree mark, while nighttime temps may plummet by as much as 40 or 50 degrees. That massive swing is due to the dry air and lack of vegetation. Without moisture to hold heat, the ground quickly radiates warmth back into space once the sun sets. But deserts aren't just about heat. One of their signature features is the dust storm known in parts of North Africa and the Middle East as a haboob. These towering walls of dust are created when cold downdrafts from thunderstorms hit the ground and push dry soil and sand into the air. These walls can stretch for miles, reduce visibility to zero, and sweep across cities like a giant erasure, blotting out the sun and coating everything in a fine layer of grit. In Australia, desert regions experience similar phenomena, sometimes with winds carrying red dust across the entire continent. And in the American Southwest, dust storms are common during late summer when thunderstorm activity peaks. Across the globe at high latitudes, the story changes dramatically. In the Arctic and Antarctic, weather is ruled by ice, wind, and extreme light cycles. Winters bring perpetual darkness and frigid temperatures, while summers are marked by endless daylight and melting permafrost. One of the defining features of polar weather is the katabatic wind, a cold, dense air mass that flows downhill from ice-covered plateaus. In Antarctica, these winds can reach hurricane force, sweeping snow across the frozen landscape in blinding whiteouts. Despite the cold, the polar regions are technically deserts because they receive very little precipitation. Most of the snow there fell thousands of years ago and has simply never melted. When it does snow, it's often in the form of tiny ice crystals drifting gently to the ground, almost too delicate to notice. It's a land of silent, elegant extremes. Now let's head to the tropics, where weather is as vibrant as the landscapes themselves. Tropical regions near the equator, such as the Amazon-Congo Basin and Southeast Asia, are home to rainforests, lush environments that receive consistent heavy rainfall year-round. Here, convectional rainfall dominates. The intense solar heating during the day causes warm air to rise rapidly, condensing into towering clouds by afternoon and producing near-daily thunderstorms. These storms are usually short but intense, releasing bursts of rain that nourish some of the most biodiverse ecosystems on Earth. The consistency of the weather in these regions helps create the conditions for dense vegetation, layered canopies, and a constant hum of life. Travel just a bit farther from the equator, and you reach the savanna zones where rainfall is seasonal. Long dry periods are followed by bursts of wet weather shaping ecosystems where grasses dominate and large grazing animals roam. The timing of rains here is crucial. Too early or too late, and entire food chains are disrupted. Island nations, especially in the Pacific, experience their own unique weather systems. Trade winds, tropical cyclones, and ocean currents all play major roles. The El Niño Southern Oscillation, or ENSO, is one of the most influential global weather patterns. During an El Niño event, warm waters in the Pacific Ocean shift eastward, disrupting rainfall patterns across South America, Australia, Southeast Asia, and even Africa. In contrast, La Niña brings cooler waters and shifts weather patterns in the opposite direction. Ocean currents, such as the Gulf Stream in the Atlantic or the Kuroshio Current in the Pacific, also regulate climate by transporting warm water from the tropics toward the poles. These currents influence coastal temperatures and weather patterns, making places like the United Kingdom much milder than other areas at similar latitudes. It's a bit like having an atmospheric heating system that brings warmth to where it's needed most. In mountainous regions like the Andes Himalayas or Rockies, elevation plays a key role. As air rises over mountains, it cools and loses moisture. This creates orographic precipitation on the windward side where rain and snow are common. On the leeward side, the so-called rain shadow. The air descends, warms, and dries out, leading to arid conditions. This is why places like the Atacama Desert in Chile, just west of the Andes, are among the driest on Earth. In coastal areas, proximity to the ocean can moderate temperature, bringing milder winters and cooler summers. Inland temperatures tend to swing more dramatically from season to season. That's why Central Asia can experience blazing summer heat and brutal winter cold, while coastal Norway, thanks to the Gulf Stream, enjoys relatively mild winters despite being far to the north. And of course, microclimates add even more variety. A shady ravine can stay cool and moist, while nearby hills bake in the sun. A city block with glass skyscrapers might reflect enough heat to feel several degrees warmer than a nearby park. A vineyard on one slope may produce different grapes than a vineyard just over the ridge. Every region on Earth has its own weather signature shaped by a unique combination of latitude terrain, ocean proximity, and atmospheric patterns. Yet despite all this variety, the underlying principles are the same. Heat rises, moisture condenses, and air moves from high to low pressure. From the driest desert to the wettest rainforest, the rules are consistent even if the results are wildly different. So wherever you are, whether you're listening to this in Hai Duong, Vietnam, where the humid air holds a story of distant storms, or standing in the still silent snow of a polar night, you're experiencing one version of the same global story, a story told in wind and water, sunlight and shadow, woven through every corner of the earth. We've spent a lot of time exploring what weather is, but how do we know what's coming? How can we predict when the next storm will hit, or whether it'll be sunny enough tomorrow to hang out our laundry? Weather forecasting might seem like a mix of science and guesswork, but it's actually a finely tuned art based on physics data and a whole lot of careful observation. It's one of the most complex tasks humans regularly attempt, and one of the most helpful. Let's start at the beginning, observing the present to predict the future. Meteorologists first need to know exactly what's happening right now, and not just in your town or even your country, but across the entire globe. This is because weather is interconnected. A thunderstorm over Texas might be part of a larger system that will eventually influence conditions in New York or even Europe. To gather this information, We use a wide network of tools. At ground level, there are weather stations dotted across the planet. These stations record temperature, humidity, wind speed, and direction barometric pressure and precipitation. Some are automated, others are monitored by humans. Every few minutes, they send their data to central databases where it's used to paint a real-time picture of the atmosphere. Higher-up weather balloons, officially called radiosondes, are released from various points around the world, usually twice a day. Each balloon carries a small set of instruments that measure conditions as it rises, reaching altitudes of up to 20 miles before eventually bursting. These measurements are crucial for understanding the vertical structure of the atmosphere, how temperature, humidity, and wind change with height. That vertical profile helps determine whether the atmosphere is stable, stormy, or somewhere in between. But the real revolution in weather forecasting came with the advent of satellites orbiting hundreds or even thousands of miles above the Earth. Weather satellites provide continuous images and data from space. There are two main types: geostationary satellites, which stay in one position relative to the Earth and provide constant coverage of the same area, and polar orbiting satellites, which sweep from pole to pole, gradually imaging the entire planet. These satellites can see clouds, measure sea surface temperatures, track hurricane formation, and even detect moisture levels in the air. They're also vital for monitoring volcanic ash, clouds, wildfires, and snow cover. Many of the images you see on weather reports, those colorful animations showing swirling clouds and approaching fronts, come from satellite data. A quirky fact is that one of the earliest weather satellites, TIROS-1, launched in 1960, only sent back a grainy black and white image, but it was enough to show cloud patterns, a monumental first step that changed forecasting forever. Radar is another critical tool, especially for short-term forecasts. While satellites provide a bird's-eye view from space, radar systems look out horizontally across the land. A weather radar sends out pulses of radio waves that bounce off precipitation. By measuring the strength and timing of the returning signals, the radar can determine where rain or snow is falling, how heavy it is, and how fast it's moving. Doppler radar in particular can detect motion within storm systems, making it invaluable for identifying rotating thunderstorms that might spawn tornadoes. All of this data, billions of data points every day, feeds into numerical weather models. These are computer programs that simulate how the atmosphere behaves based on the laws of physics. They divide the world into a giant three-dimensional grid, with each cell representing a small chunk of the atmosphere. Within each cell, the model calculates how temperature, pressure, moisture, and wind will change over time based on surrounding conditions. The process is incredibly complex. Each weather model runs on powerful supercomputers, churning through equations that represent atmospheric dynamics, thermodynamics, radiation, cloud formation, and more. There are several major weather models in use today, including the GFS Global Forecast System in the United States and the ECMWF European Center for Medium-Range Weather Forecasts, each with its own strengths and weaknesses. A common historical fact is that the first successful numerical weather prediction was made in the 1950s, using one of the world's earliest computers, a feat that laid the groundwork for all modern forecasting. Despite the sophistication of these models, forecasts still involve a degree of uncertainty. The atmosphere is what scientists call a chaotic system. Small differences in initial conditions can lead to big changes in outcomes. This is the essence of the so-called butterfly effect, the idea that a butterfly flapping its wings in Brazil could set off a tornado in Texas. It's a poetic way of saying that even tiny measurement errors can grow into large discrepancies over time. To manage this uncertainty, meteorologists use ensemble forecasting. Instead of running a model once, they run it dozens of times with slightly different starting conditions. The result is a range of possible outcomes, which can then be averaged or analyzed to understand the most likely scenario. If all the model runs agree, the forecast is considered high confidence. If they diverge, it's a sign that the situation is more unpredictable. Forecast accuracy has improved dramatically over the past few decades. A 3-day forecast today is roughly as accurate as a 1-day forecast was in the 1980s. 5-day forecasts are pretty reliable, and even 10-day forecasts, while less precise, can give a decent sense of trends. Still, the farther out you go, the blurrier the picture becomes. Tiny uncertainties multiply, and the exact timing or location of events becomes harder to pin down. Short-term forecasts, sometimes called nowcasting, are especially useful for predicting rapidly evolving events, like thunderstorms or tornadoes. These rely on high-resolution radar local observations and updated models that run every hour or even more frequently. Meteorologists use this data to issue watches and warnings, helping people stay safe during severe weather. There's also a growing interest in probabilistic forecasting. Rather than saying, "It will rain tomorrow," a forecast might say, "There is a 70% chance of rain tomorrow." This approach reflects the true nature of the forecast. It's not a guarantee, but a likelihood based on current information. Probabilistic forecasts help people make better decisions, whether that's packing an umbrella or rescheduling a picnic. Beyond predicting tomorrow's weather, forecasting plays a huge role in aviation, shipping, agriculture, emergency management, and energy production. Airlines use forecasts to plan flight routes and avoid turbulence. Farmers depend on rainfall predictions to irrigate crops. Utility companies adjust their systems based on expected heat or cold. And emergency responders use forecasts to prepare for hurricanes, floods, and wildfires. Weather forecasting is also expanding into the world of machine learning and artificial intelligence. These technologies are being used to analyze vast data sets, spot subtle patterns, and improve model accuracy. While they won't replace traditional forecasting anytime soon, they're becoming valuable tools in the meteorologist's toolkit. Historians still debate whether the first modern weather forecasters truly saw themselves as scientists or simply as observers of a complex natural system that was largely beyond human control. And finally, let's not forget the distinction between weather and climate. Weather is the mood of the atmosphere, what it feels like today or tomorrow. Climate is the personality of the atmosphere, the average of all those moods over a long period. Climate has never been perfectly stable, but what we're seeing today is different. The changes are happening faster and are being driven primarily by human activity. Since the late 19th century, the average global temperature has risen by more than 2 degrees Celsius. This warming is largely due to the greenhouse effect, where certain gases like carbon dioxide from the burning of fossil fuels trap heat in the atmosphere. This warming doesn't just mean warmer summers. It means changes in weather patterns all around the world. We're seeing more frequent and intense heat waves, more extreme rainfall events, and stronger hurricanes. The balance is shifting. A quirky little-known detail is that as the Arctic warms faster than the rest of the planet, the temperature difference between the poles and the equator weakens. This can slow down the jet stream and make it wobble, leading to unusual weather patterns. A slower, wavier jet stream can cause weather systems to stall, meaning a rainstorm might linger over the same region for days, or a heat wave might lock in place. So the next time the sky darkens unexpectedly, or the summer feels just a bit too long, remember, you're witnessing not just weather, but a chapter in the larger story of a planet in transition. And so we've drifted through the winds, and the rains floated with clouds, and stood in the quiet hush of falling snow. We've explored lightning-lit skies, watched deserts shimmer in silence, and traced the invisible hands that guide our weather from one side of the world to the other. From gentle fog to towering hurricanes, from the science of sunlight to the whispers of wind, we've uncovered just a little of how this beautiful, chaotic, ever-moving system works. Weather is more than just background noise. It's a conversation between earth, ocean, and sky, a language of temperature, moisture, and motion, written in clouds and spoken in thunder. It shapes the landscapes we live in and the lives we lead. It brings harvests and hardships, calm mornings, and wild afternoons. And despite all our instruments and satellites and models, it still finds ways to surprise us. As you close your eyes tonight, tucked in wherever you are, the atmosphere keeps moving. Wind flows silently over mountaintops. Raindrops gather on leaves. Somewhere far away, a snowflake is beginning to form. It's comforting in a way to know that the sky never truly sleeps. It simply shifts, reshapes, and continues its slow dance above us. And before we part ways, let me ask again. Where in the world are you listening from? What time is it where you are? Midnight 2 in the morning, a quiet afternoon with the curtains drawn. Wherever and whenever you are, thank you for being here, for winding down with me and joining this journey through the science of weather. Now rest well. Let your thoughts drift like clouds, and may your dreams be as soft as fog and as bright as a morning after rain.